I'm here to introduce the speaker. First, a couple of announcements. First, I want to thank Kristen, who's in the back there, for doing all the hard work for making everything possible for this event. So, thank you back there with your camera. And also, up in the corner there by a little poster display is a sign-up sheet. You can sign if you'd like to receive email announcements about other public events sponsored by our department. So tonight's special guest is Brian Fields, who is actually at the center of something that's been a very big event in the news, in the science news the last few weeks. It is really a very nice coincidence that he's here now, just in the wake of all this publicity. We didn't really plan it that way, it just kind of happened that way. Brian got his PhD from the University of Chicago in the 90s, and after moving around a bit, he ended up at the University of Illinois, where he is the chair of the Astronomy department. So, here we are. Brian? All right.
Oh, thank you. You haven't heard what I have to say yet. But thank you. Thank you, Adrian. I want to thank the physics department for your kind hospitality. Kristen, for making all the demos you're going to see tonight possible. And thank you all for coming out on the blustery night towards the end of the semester. So I appreciate your coming, and I hope if nothing else to make it entertaining. So just as Adrian said, this is a fun time for us because I want to tell you about what happens when stars attack. So I'm not talking about Christian Bale or Mel Gibson or other ill-behaved Hollywood celebrities. I mean actual astronomical objects exploding near the Earth. And so we'll unpack what all of that means, and there'll be demonstrations and bad jokes. And this is also a chance, I imagine there are people here who aren't scientists for a living, and this is also a nice example of how science works, that there's different kind of styles of science, and I have a short attention span. I work on a number of topics, and this is something that started out as a hobby that I worked on when I was a graduate student, 2 decades ago. And it was sort of a fun thing to do on the side because it was a new field. It was something that we were doing for the first time, and no one had figured out even the basics. And it's gotten more interesting over time, and I'll try to give you a sense of why it was a disreputable hobby at the beginning and how it's become more interesting, particularly recently. All right, so we want to find out tonight what happens when stars attack. And so here's the game plan. So first, I'll show you that exploding stars are brighter than 1 billion suns. These are otherwise known as supernova explosions, and I'll show you what they look like. We can see them now in distant galaxies, and we know that they occurred in our own galaxies in the past. So we'll talk about the present and past of exploding stars. And then we'll talk a little bit about how they work. It's one thing to see these beautiful objects in the sky. They're sort of like fireworks. Fireworks are amazing, but we'd like to also understand, well, how do they actually work? Get under the hood and see what what makes them tick. And it turns out that supernovae and the stars that give rise to them are the celebrities of the cosmos. They're the rich and famous and the few. So we'll talk about their celebrity lifestyles. They live extravagant lives and leave a big mess when they die. And so we'll talk about that, how they die, how they flame out. And then we'll bring the problem a little closer to home. So what happens if one of these incredible explosions isn't far away and it's some beautiful fireworks that's gorgeous to look at, but what happens if it's really close? And there comes a point where it's not funny anymore. And so we'll talk about how close is too close for comfort. And then finally, we'll say, well, did this ever happen? These stars explode throughout the universe and throughout our own galaxy. Has anyone ever exploded near us? And how would we know? And it turns out the way you know is supernova archaeology. It turns out a supernova close to us could leave its traces under the ocean in the deep Pacific. And so we'll talk about that there's actually evidence that this occurred. So if you're willing to take my word for it, then we're done. That's what we're going to talk about. But if you want to stay along for the ride, I'll explain what's behind all of this. So first things first, we have to talk about what supernovae are. So we'll talk about what it looks like to see an exploding star. This, for example, is a gorgeous image. You'll see a number of gorgeous images of exploding stars, so I just should pause and say the beauty of astronomy is this is data. So this isn't just beautiful, it's data. So this is a star called Cassiopeia A. This is something, it's a former star. It exploded about 300 years ago. And the picture you're seeing here is actually in false color. If you looked up in the constellation Cassiopeia tonight, you will not see this. Because you're here on the surface of the Earth and your eyeballs don't see X-rays. But if you went above the surface of the Earth and put on X-ray goggles, X-ray vision, then this is what you would see. So this thing is crackling with X-rays, and so what this is telling you is this is hot gas, so hot that it's not red hot or white hot, it's X-ray hot, which means it's millions of degrees, and this was expelled from a star 300 years ago, and it's still millions of degrees, and then there's this little dot in the middle, and that's an interesting crunchy center, and we'll get to what that is. So these things are amazing. All right, but to get us on the same page and to get you in the mood, so let's talk about stars and talk about their fate. So here's a particularly nice star. This is our all-time favorite star. That, of course, is the sun. And that's a beautiful example of a star. So let me get you in the mood by reminding you about a few important facts about stars and about life in general. And none of this is going to come as a big shock to you, but hey, bear with me, I'm building to something. So first of all, stars like the sun constantly lose energy, which is to say they constantly spread energy out into space, generally in the form of light. So sunlight lands on the Earth, it warms the Earth, it lets the plants grow, we love sunlight, it's very good. But obviously sunlight is a form of energy. Ultimately, most of the energy we have on Earth and fossil fuels and everything ultimately traces back to sunlight. So stars absolutely, not just the sun, but all stars, are constantly spewing light energy into space. So this is not big news, I know, but like I said, we're building to something. Another fact, stars have finite mass. That is, the amount of stuff, that's what all mass means, the amount of stuff in stars is finite, by which I simply mean it's not infinite. Fair enough. So stars like the sun have a lot of mass, a lot of stuff, but not an infinite amount of stuff. Fine, that's not a surprise, but that means whatever their fuel supply is, at the moment we don't even care what it is, turns out it's nuclear fusion, but it doesn't matter, whatever the fuel is, there's not an infinite amount of it, and so that means they've got a limited amount of stuff they can make into energy, a limited amount of fuel, limited amount of energy supply. Fair enough. Again, not a big shock to you that stars have finite mass, but okay. And then finally, a very important principle of physics is that energy is conserved. So in an isolated object like a star, you can take energy and change it from one form to the other. You can move it from one place to the other, but you can't just make energy out of nothing. You actually can't destroy it either. You can change its form, but you can't make it or destroy it. You can only move it around. The Twitter version of that is there's no free lunch. Can't get energy out of nothing. So now none of these are terribly controversial facts. Stars always lose energy, they have finite mass and thus finite energy supply, and energy is conserved. So none of those are big shockers, none of those are anything new to you. But if you string those 3 points together, they have an interesting and inescapable consequence. And now we go to the audience participation part of the evening. There'll be more than one. So what does this mean? Don't be shy, it's not a trick question. Stars are going to die. All stars, including the sun, are doomed to die because they're throwing out energy all the time, they're not making more, and so they're going to run out at some point and they are going to die. So I'm going to start you off with a big bummer because I'm telling you that stars can't live forever, which means all stars must die. I should point out that there's even a little bit more to this. So all stars must die. They cannot live forever. But it is also true that there are stars in the sky now. And the fact that there are stars in the sky now then means, on top of this, stars also, thank you very much. Stars, checks in the mail, stars also have to be born, which means stars have life cycles. They're born, they die, they're like people, animals, plants, they have life cycles. So stars, like people, have life cycles. That's amazing. And notice, this is sort of the beauty of astrophysics, because we've actually just now done a little bit of astrophysics. So we took something about the laws of nature that we know, made a few relevant observations, strung them together, and we come to this really interesting conclusion. Based on these seemingly trivial facts, we discover that stars have life cycles. That's the beauty of astrophysics. That's how the game is played. All right, so now, stars have life cycles. Amazing. All right, so now let's move on to supernova explosion. So stars live their lives and die, but let's talk about what supernova explosions are like. So supernova explosions aren't the way most stars die. So first of all, it's in my contract that I have to immediately make it clear the sun is not going to die in a supernova explosion. So you might read some science fiction stories to the contrary. That's all good fun, but that's not how it works. I just told you the sun's going to die, and it is, and I'm sorry about that, but the sun won't die this way. Oh, wait, another thing in my contract I forgot to ask. There's a really important question. I just told you the sun is going to die. So wait, there's an important follow-up question that someone should ask me.
How soon?
How soon? Exactly so. So notice, I proved to you, you proved to yourself that the sun is going to die, but that proof didn't say anything about how long until that happens. And the good news is we have a good long while. The sun is middle-aged, like many of us, and as a result, it's about halfway through its life, and which is to say it's lived for about 5 billion years, and it's going to live for another 5 billion years. So don't make appointments for after 5 billion years, either that or, you got to get a U-Haul and move, but until then, we're fine. So.
But how long until it becomes impossible to live on Earth?
But we have a ringer in the audience, Adrian Malat, who introduced me, who's an expert on this and points out that the Earth will become a difficult place to live in merely 1 billion years. So the truth is, don't mark your calendars for any time after 1 billion years. Okay, but so the sun will die in a very interesting way, but not in an explosion. But to have an explosion, you need something that's about 10 times the mass of the sun, maybe just 8 times the mass of the sun, but something a lot more massive than the sun, a really massive star. And such stars exist, and when they die, it's spectacular, but it's also rare. About 1 in 1,000 stars, if you went out and pick a fair sample, about 1 in 1,000 stars with this kind of very massive star. And as we will see, they're crucial for life as long as you don't get too close to them. So what do we see? Well, as astronomers, what do we actually see when we turn our telescopes to these things? And so let me give you a sense. So this picture here is a beautiful, beautiful image, and it has 2 interesting features in it. So first, you'll see there's this big swath of light here. So this big glowing swath of light and little dot here. Let's first talk about the swath of light. The swath of light is a galaxy. So what you're seeing here is a system of something like 100 billion stars. And they're all clumped together by their own gravity in a thing we call a galaxy. This is a faraway version of the thing we live in called the Milky Way. And so this thing contains 100 billion stars, and it's so far away that I think this is a Hubble telescope picture, and even the Hubble telescope can't they can't make out the stars individually. All of their light gets smeared together. So this white smear of light is in fact the combined light of something like 100 billion stars. So it's there you go, combined light, 100 billion stars. So that's what all you're seeing here is. So that draws your eye. That's a beautiful thing. It's an amazing thing that the universe is organized into galaxies. There's a whole talk you could hear about that. But I want to focus on the other dot of light. That's this. This is the light from a single star, one star, which is dying as a supernova, and it's become very bright. And as you can see, if you kind of squint, you can see the light from this one exploding star is about the same total amount of light as all of these other stars put together, which tells you this one exploding star is about as bright as 100 billion suns. That's pretty impressive. These are really powerful explosions, really spectacular. All right. So they're bright. That's what I mean by bright. They can outshine a galaxy. They also change rapidly in time. So this is very spectacular. This was back in I believe 1994, and if you go look now, there's going to be nothing there. So this thing gets bright over a period of weeks and months and then becomes dim again, and if you look at it now, you would see nothing there unless you looked very, very, very carefully. And so here is a little movie. So here is a different nearby galaxy, and right around there is a loop around, I believe. There we go. You can see the supernova exploding. You can see all the rest of the stars in the galaxy. And then what's shown here is a little graph that shows you how bright it is over time. And it gets really bright, and then it gets dim, and then it continues to get dim. And if you spread it out into its different colors, you get different amounts of different colors. And the experts in the room will say, these different features actually tell you something about what the thing is made of. But we'll get to that. All right. Beautiful. So, and all of this happens over a period of weeks. So these things become very bright and then very dim and then they're gone. So they're like fireworks. They blow up, they're really spectacular, and then they go away. Okay, great. Now, and when something this powerful, this like a bomb, we're going to get to how it's like a bomb, but these explosions launch a blast wave and fling the material of the star out into space and leave these tendrils of hot gas spread out over space, and if you look at it thousands of years later, you can still see the hot gas, the remnants of the hot gas strewn out over space and glowing. And so that's what you're seeing here. This is something that's thousands of years after the explosion. So it's a different supernova, and it's thousands of years afterwards, and you can still see its traces. All right, great. So I already showed. So that's an even closer up view of the same picture. So just to give you another idea, so these are just beautiful images, so it's just fun to look at them. So this is a particularly spectacular one. This is called the Crab Nebula. More about this in a minute. And you'll see there's an interesting swirly thing in the middle. So that's, we'll get to what that is. And then here's another view of the thing I was showing you before. So you can see all these gorgeous tendrils of gas. And this is now a very, very big bubble blown out by this amazing explosion. Okay. So supernova explosions are rare. Like I said, less than 1% of stars die this way. In fact, 1/10 of 1% of stars is roughly the number, die this way. So it's quite rare. The sun won't die this way. Most stars in our galaxy will not die this way. And in fact, none have been seen, I should say, have been seen by humans in our galaxy for 300 years. This thing I showed you at the beginning, 300 years ago, that's the most recent one that we know for sure about. So the sun will die, but not this way, not in an explosion, and not for billions of years. So again, please don't, there are things to worry about in this world, but not the sun dying. Okay, all right. But in recorded history, I told you there hasn't been a supernova for 300 years, but people have been around and writing things down for much longer than 300 years, so we actually have records of supernovae. A famous example is in the year 1054, so we're coming up to not quite 1,000 years ago, so this is not Y2K, this is Y1K. There was a supernova, and the really interesting thing is there's no written record of this in Europe. There were lots of people in Europe at the time, and they certainly knew how to write, but nobody wrote down any record of it. It's very peculiar. I mean, there's speculation about why they didn't write anything down. But in China, people perfectly well did write it down. Now, I don't read Chinese, but so here's their journal at the time. This was the Royal Astronomers, and they noticed this, and they had this is their version of their journal. This is what we would now today call the Astrophysical Journal, and they have this little section here, which people in the know can tell you that's where they're reporting this thing. And I love the name they give for it. It's a beautiful name. They call it a guest star. It's very welcoming. I like that, particularly given how nasty these things really are. They called it a guest star. So the Chinese saw it, but it's not just in China that it was seen. The Native Americans, the Anasazi people in New Mexico, also saw it. So the Anasazi had this amazing civilization in New Mexico. They were great astronomers. They didn't have telescopes, but they watched the skies very carefully. And this is just a small piece of one of the places they lived. And there are these interesting rock paintings. So there's this star-like thing, there's a crescent moon, and a hand. And I'm no anthropologist, but my understanding is the hand is like a way of saying this is significant. And then there's this bright thing next to the full moon. And it turns out from the Chinese records, you can work out, yeah, this thing should have appeared near the full moon. So it looks like the Native Americans saw it, the Chinese saw it, and it's an interesting question why no one in Europe wrote it down. So that's what it was like 1,000 years ago, and if you look at it now, this is actually the thing I already showed you a picture of. So this is what it looks like now if you look in the same region of the sky. So this is a thing called the Crab Nebula, because it looks sort of crabby, and this is the remains of an explosion 1,000 years later. All right. So another example one other recorded history example is this thing, which is from 1572. And this was discovered by the great astronomer Tycho Brahe, who's this great Danish astronomer, and one of the founders of modern astronomy. And this is his chart where he's showing you where to look in the sky to see this thing. And it's hard for you to read this, and it's in Latin anyway. And in Latin, he refers to this thing as a new star, nova stella. Very nice. So not guest star, but new star. And then he wrote about it. The beautiful thing is that he wrote about it. So now we have an eyewitness account. So, and we'll show you the eyewitness account, but just for fun, if we go to this same region of the sky today, if you just look with your naked eyeball, you won't see anything. But once again, if you get your X-ray vision and go look with the appropriate NASA satellite, this is what you see. So you see these gorgeous X-rays, which again, this tells you the fact that this thing is crackling with X-rays means that there's gas that's been heated to millions of degrees from this explosion. It's hundreds of years ago, and it's still millions of degrees. You can imagine how violent this was. Okay, so the great thing about Tycho is he actually wrote down, he was a great astronomer, and one of the things you do in science is you have to record your results. And so he wrote a beautiful description. It's a first-hand description of a supernova. So if you don't mind, for dramatic effect, I'll read it for you. So he writes, on the 11th day of November, in the evening after sunset, I noticed that a new and unusual star, surpassing the other stars in brilliancy, was shining. And since I had from boyhood known all the stars of the heavens perfectly, it was quite evident to me that there had never been any star in that place of the sky. I was so astonished of this sight, a miracle indeed, one that had never been previously seen before our time in any age since the beginning of the world. I love this passage. And what's great about it is like all good scientists, Tycho was pushing the edges of what we knew, which means he got some things right and he got some things wrong, and that's still true today. And so a fun thing is, let's give him credit. He was a brilliant guy. What did Tycho get right? There's some key observations that are absolutely right. He's bang on the money. So again, audience participation. Please. You bet. Thank you very much. He says it was unusual, surpassing the other stars in brilliancy, and that is exactly right. He knew exactly how bright they were, and no doubt about it, this was way brighter. Exactly right. Thank you very much. There's other things that he gets right. Anyone? Please. Yeah, that's right. So it hadn't been there before, so it was new and it was very bright. That's exactly right. And there's another thing. So the astronomers in the room will actually know this. He also says, well, I'll show you. So let's give him credit. Let's give him a score. So it was unusual, it was new, it was bright, and he did also know the heavens, the stars, the heavens. He was a very, very good astronomer. He wasn't a modest guy, but he was a very good astronomer. All right. On the other hand, Tycho, as brilliant as Tycho was, he did get some things wrong, and it does no disrespect to him to point out what he got wrong. So what did Tycho get wrong? See it. Yeah, so there was a star that I'm not quite sure how to grade that, because he probably couldn't have seen it with his naked eye, so it's kind of not his fault. But of course, there was a star there, which actually means, yeah. Oh, so I'm sorry, but there was another. One that has never been previously seen. Yeah, never been seen since the beginning of our time. Like, how does he know that? He wasn't here since. That's just arrogant, right? Because I just showed you, 1,000 years before, 500 years before this, exactly the same thing had happened. So that's just him being arrogant. That happens in science too, I'm afraid. And then there's one other thing. He said there hadn't been a star before there, and then there's one other slight thing. Let me point this out to you. All right. So, again, never been any star, never been previously before. That's just wrong. He also said this was a new star. So actually, he's right that it changes the number of stars, except it doesn't add a new star. In fact, because it's something dying, it subtracts the number of stars in the universe. This is what we refer to in physics. The fancy name for this is a sign error. We do this kind of thing all the time. So he just made a sign error. It does change the number of stars just by the wrong amount. Okay, very good. All right, so far so good? You guys have been great. So good. Please just don't be shy. Ask me questions. We're a small group here, so don't be afraid to ask me questions if things don't make sense. All right. So that being the case, we shall move on. So all right. So now we're up on how gorgeous supernovae are when you see them, but now let's get a sense of how they work, because we want to not just observe them, we want to understand them. So let's get a sense of how they work. All right. So we want to get under the hood in the sense of, like in your car, getting under the hood, tinker with it, and see how it runs. All right. So this is computer simulations are important to this game. That's what that is. So supernovae are the James Dean of stars. And the young people in the audience won't know who James Dean is, but the thing you need to know about James Dean is this guy from the 50s, and he lived fast, he died young, and he left a beautiful corpse. So let me tell you a little bit about, so they live fast, die young, and leave a beautiful corpse, and so let me tell you how that goes. So the life of a star, not just of a star destined to be a supernova, but all stars, their lives are a struggle, a constant struggle against their own gravity. Stars are these amazingly massive objects. There's all this mass, and mass itself is the source of gravity. So after all, the sun has enough gravity that it reaches across space and keeps Earth in orbit around the sun. Indeed, it keeps all the planets in orbit around itself and keeps us from wandering off into space, and we can be very grateful for that, because if we did wander around, it would get very cold. So if the sun has enough gravity to hold on to the Earth, what about the sun pulling on its own self? It turns out as you get closer to a source of gravity, the gravity gets even stronger. So the sun is also pulling on itself, and not just the sun, all stars do this. And so, since the sun is pulling on itself, in fact, a good question would be, wait a minute, why the sun is made of gas, and as we know, gas is something that you can move around in space. It's not a solid, you can move it around, you can make it flow, and you can compactify it, you can compress it. And so a fair question is, wait a minute, why doesn't the sun just collapse under its own gravity? And indeed, that's a very good question. In fact, if there weren't something to prevent this, the sun would collapse under its own weight. In fact, it would keep going all the way to becoming a black hole unless something stopped it. Once again, I don't want to leave you in fear, so the sun is not going to become a black hole because there is something fighting against gravity. So let's talk about what that is. I believe that's the next line. Yes, so what happens is the thing that keeps the sun fighting gravity is the fact that it's hot. So the sun is hot, I think we can agree with that. It's very hot, and because it's very hot, the gas in the sun is under very high pressure. It's high pressure gas. And the high pressure of the gas is pushing out and holding up the weight of the star. And so to give you a sense, if stars are too complicated to understand, they're so big and exotic, if you can, something that's very much like a star is a balloon. So this is what we physicists refer to as a balloon. So filled with air, I blew it up right before the talk started. And so it's actually a very similar situation. So the balloon so it's a bunch of gas. And then it's surrounded by this elastic, right? And as you know, elastic pushes inwards, and gases are things you can compress, and so you might say, well, wait a minute, why doesn't the balloon collapse all the way down? Why doesn't the elastic force crush the balloon down to nothingness? Well, it doesn't because air pressure, of course. There's air inside, and it's pushing back, and that causes the balloon to be nice and stable. Well, it's actually, if you can understand a balloon then, a car tire works by the same principle. If you think about it, your car is sitting on a bunch of air because it's sitting on a tire and the tire itself is full of air. Why doesn't the axle of the car slam down to the road? It doesn't because there's air pressure in the tire. So car tires, balloons, and stars, it's all basically the same stuff. Except for stars, the thing that's pushing inward is not the elastic force of a balloon or the weight of a car, it's actually the gravity of the star itself. Other than that, basically the same. But then that leads to an interesting question. What would happen if the fuel runs out? So if the star is being heated up and nice and pressurized by the hot gas inside of it, what would happen when the fuel of the star runs out? Yeah, there we go. I saw it. Yeah, I got a collapsing motion. That's exactly right. And that is something that's worth testing. So I told you that a balloon is like a star, so I can't easily take a star and make it run out of fuel, but I can do an experiment with a balloon. So let's do an experiment with a balloon. So what I'm going to do is I'm going to take the balloon, which is full of nice air that's room temperature and so is nice and warm and pressurized. And what I'm going to do is cool it off. And the way I'm going to cool it off is I'm going to dunk it and put it at a temperature of minus 321 degrees Fahrenheit. So that's cold. And the way I'm going to do that is that's what this thing is. So this is a fancy, a physicist version of a thermos. See, it's very nice. Bubble, bubble, toil and trouble. So this is liquid nitrogen. And so it's nitrogen, which is actually we're breathing right now, but cooled down to very, very cold temperatures. And it's pretty cool stuff. So it's hard for you to see out there, but I think if I do this right, there's a little camera here to help you see what's going on. Good. So, so this is a camera that's pointing down so you can more easily see what's going on. So I'm going to take this, and first of all, just because liquid nitrogen is cool, let's just pour some of the liquid nitrogen in here. Okay. And it's minus 300 degrees, 320 degrees Fahrenheit, and you can see it's boiling away. And it's boiling away because it's very unhappy to be in a room that's as warm as this. And so it's boiling away and turning into a gas. That's what all this smoke is. And pretty soon it's going to all be gone. So this is impressive stuff. This is very cold. And so what I'm going to now do is see what happens if I subject my balloon, my star, to running out of fuel, which is to say becoming cold. So we'll put the balloon in there, and let's make it cold. There we go. So I don't know how you can see. It's having a hard time. Yep, there it is. And there we go. So as you can see, the balloon becomes very small, but here's the really neat part. Once you take it out of the liquid nitrogen, it can warm up again, and it's reversible. It goes right back to being a nice round balloon. And you can do it again. So there you go. So the exercise is you take the balloon, you cool it down, you remove its pressure support, and lo and behold, it collapses. And if you can understand a balloon, you can understand stars. So here we go. Afterwards, you want to come up, we can play more with the liquid nitrogen. Okay, so great. So stars live fast, and then they die young. So the idea is, once a massive star exhausts its fuel, it does what the balloon did. It collapses. It runs out of its heat source, and it collapses. And then So the thing literally collapses under itself. Suddenly there's nothing to fight against gravity. Remember, a star's life is a struggle against gravity. Nothing stops it. So the star collapses under its own gravity and gets crushed by its own gravity. And the center of the star becomes denser and denser and denser until finally the center of the star becomes ultra dense. It actually becomes solid, an extremely dense solid called proto-neutron star matter. And then the rest of the, so when the thing that collapses first is the very inside of the star, and then the rest of the star falls down on top of it, and it feels all the intense gravity, so it slams down at a goodly fraction of the speed of light, maybe 10% of the speed of light, slams down onto this newly created ultra-dense solid and bounces back. And then that bounce is a pretty interesting thing. That's what the little arrow is trying to hint at. And there's a shock wave launch, and the inward motion gets turned around to become outward motion, and there's an explosion. And that's so cool, that's also worth a demonstration. And so I'm happy to say I brought a supernova with me. No need to be afraid, because this is publicly, commercially available. It's called an astroblaster, and it works like a real supernova. So it says right on the box. You can go, I'm not trying to sell you anything, but you can go buy one. So I've got one with me. So here's the astroblaster. This actually doesn't represent the entire supernova. This is the outer layers of the supernova that are going to collapse down on this incredibly dense core, collapsed core of the supernova. And then there's a safety feature. Only the red ball at the top can come off, and then there's a safety feature, safety first, that the rest of it won't come off. And so to simulate a supernova explosion then, you have to imagine that this was sitting on top of a star that was perfectly nice, pressurized, and stable, but then the star ran out of fuel, basically did what just happened to the balloon. It runs out of fuel, collapses upon itself, and then suddenly the outer layers of the star say, wait a minute, there's nothing underneath me, and they fall too until they hit the solid, crunchy center, ultra-dense solid of the core of the star. And then the inward motion becomes outward motion, and let's see how that goes. So the star burns, runs out of fuel, collapses, and then 3, 2, 1. Yeah, so there it went. It shot across the room, and maybe we'll find it, maybe we won't. There it is. All right. So you see that, in fact, it launched so fast you couldn't even follow it with your eyes. At least I couldn't. I don't know if you could. But you get the idea that the explosion is rather powerful and launches things with rather high speeds. So that's pretty impressive. So we get this amazing explosion. And then what's left behind? And what's left behind is a beautiful corpse. So we live fast, die young, and leave a beautiful corpse. So there's an ultra-dense center, which is either a crazy thing called a neutron star, or actually you can get a black hole out of this as well. And But most of the material in the star, most of the stuff that was once inside the star gets spewed out into space at very high speed. That's the red ball. And again, this is the picture I showed you before, and this is all this stuff that's millions of degree gas left over from a star that exploded 300 years ago. And this is gas from a star thousands of years ago, and it's still glowing left over from the explosion. And so this is important. This is not just of interest for general curiosity. Our lives depend on this. And this is because this is the astronomer's circle of life. I understand there are other contexts for this, but for astronomers, what astronomy has taught us is that the universe is filled with gas of various types. Here's a gas cloud. And the gas clouds collapse under their own gravity under the right conditions. Now we're zooming in and we see these great pillars. They look like clouds because that's what they are. And at the little tips of the fingertips here, those are where newborn stars are being formed, collapsing under their own gravity. They live and die, and a small fraction of them die as supernovae. Here's a supernova exploding. And then what's left behind is one of these neutron stars or maybe a black hole. But most of the stuff that was once in the star gets spewed out in the form of very hot gas, mixes with other gas that was already there, and we cycle around again and again. And over time, stars add more and more of their guts to the rest of the universe. And so what that means is that we are made of the ashes of stars. So this process happened process happened for billions of years before the birth of the Earth, and we are made of the ashes of stars that lived and died, supernovae in fact, that lived and died before the Earth and the solar system were formed and enriched the material of the formation of the solar system. We are the children of supernovae. So supernovae are absolutely essential for life. We could not exist without them. So to be a little bit more specific, what's going on, I mentioned this before, in the very hot cores of stars, what's really generating the heat in the star are nuclear reactions, atomic nuclei crashing into one another, generating new nuclei, nuclear fusion. And most of these nuclear reactions produce healthy, stable atoms, but in the blizzard of nuclear reactions, all the different nuclei slamming into each other in the billions of degree temperatures centers of these stars, some unstable radioactive atoms are produced and then decay over time. Radioactivity is all about decay. It's about instability. And so that leads us to one more demo. And this is the radioactivity demo. So let's see if I can make this work. Great. So this is a Geiger counter. So as you probably know, if you've seen in movies, so this measures radioactivity. So every time, so what is radioactivity? So let me step back. So what is radioactivity? So again, there's a long physics story here, but basically some kinds of atoms, or really the nuclei of atoms, the very center of atoms, mostly they're stable and they'll sit around forever and you're made of stable things and it's all good. But it is possible to have some kind of atoms that are unstable, and they're not really happy with their identity. It happens to all of us. It's one time or other we're not happy with who we are, and what do you want to do? You want to change. And so that happens to unstable atoms as well. They want to change their identity from one kind of atom to another kind of atom, and so to do that they have to undergo this process of change, which is called radioactive decay. And various kinds of nuclei do this, and they do this with different kinds of rates. Some do it very rapidly, they really want to change in a hurry, and some take a while to change, just like with people. Okay, so, and what this Geiger counter does is it measures when there are radioactive decays, that it emits energy, which this thing can measure, and then you hear a click. There's not much going on now, but I have a dangerous radioactive source. It's not dangerous, it is radioactive. This is actually, this is something you can go buy yourself. These are, if you like camping, these are mantles, little socks that you put around camping lanterns, and it turns out that they have a little bit of the element thorium in them. So it's thorium, which is named after Thor, which of course is famous from the comic books and movies. And instead of having a hammer, it has radioactivity. And so there's a little bit of radioactive thorium in here. It's a tiny amount. It's absolutely not dangerous. I would not be monkeying with this if I thought it were dangerous. But in fact, the radioactivity is so weak that if I put the thing on top of it through the plastic, it doesn't sound very impressive. But if I put it on the inside, now let's get it to do it. There we go. I don't know if you can hear that. So every one of those clicks is a radioactive decay from the trace amounts of thorium in this thing that you can go buy in the store yourself. All right, So that's a particular kind of radioactivity. So this thorium thing is unhappy. It doesn't like its station in life, and eventually it's going to become lead, and then it's going to be happy. So it's on its way to becoming lead. So we wish it well. So all right. So and so supernovae don't just make stable things; they make unstable things that decay. So for example, when the solar system was born 4.5 billion years ago, there were traces of radioactivity when the solar system was born. They've long since gone away, but we still have them. And there are a few things that have lived so long we still have them, like the thorium here. And actually today our entire galaxy we know contains traces of radioactivity because we can see it. So this is a beautiful picture. This is a picture of the entire sky. So I've taken the entire sky, which is a sphere, and I've kind of smushed it out on a plane here, so I'm sorry about that. But it's a very special picture. Again, it's false color. It's not what it looks like to your eyeballs. But it turns out there's a particular kind of radioactivity that emits little flashes of light, very particular flashes of light called gamma rays. In fact, a very particular gamma ray. And this is tuned to look at just those kind of gamma rays. And this gamma rays and the radioactivity comes from a particular radioactive form of the element aluminum. So the same aluminum that's in your beverage cans, which is perfectly stable, there's a variety of it which is not stable, called aluminum-26, and that's what that is. And so those flashes of light are telling us that our galaxy contains this crazy radioactive aluminum that was made in exploding stars. For some reason we're having a rerun here. So as cool as that is, we don't have to do it twice. So, all right. So far so good? All right. Okay, so now we're moving along. Things are accelerating. So we know how awesome supernovae are to look at. We understand a bit how they work. They're massive stars. They make all kinds of elements. They're element factories. So now, what happens if one of these things gets too close to the Earth? So, all right. So supernova explosions near the Earth, there's no other way to talk about it. They are cosmic weapons of mass destruction. But mass destruction is nothing to joke about, but it's the only standard of comparison. Now, in our Milky Way galaxy, these things are rare. There's about one supernova a century, maybe 2 or 3, and most are far away. So in an entire galaxy like ours, this is not ours, but this is what ours would look like if you could fly away from it. In our entire galaxy of 100 billion stars, you get about 1 per century. They're all across the galaxy, and typically they happen very far away. And particularly right now, there are no supernova candidates near the Earth. They would be very massive stars. They'd be very obvious on the sky. There are none. But over the history of the Earth, which has lasted a good long time, 4.5 billion years, there are very likely many events that are near the Earth. And once you realize that, it is really possible, not so much for us, but for our ancestors, and maybe our ancestors a long time ago, so bacteria, that there were supernovae over the past history of the Earth. The question is, how can they be dangerous? If one of these bombs blows up near the Earth, how can it be a biohazard? And indeed, they can be dangerous. In fact, Kansas is one of the world capitals of studying this problem. Professor Malott, who introduced me, Brian Thomas, who's a KU grad and works just down the road, and Drew Overholt here, also from just down the road, also a KU graduate. So they all are the world's experts in why a supernova can ruin your entire day. So really, they should explain, but I'll summarize and let them correct me if I get it wrong. So these things can be very dangerous, and the holy grail or unholy grail of this would be to connect a supernova explosion with a mass extinction on the Earth, a great die-off of species. And so the dinosaurs are an example of a mass extinction, not caused by a supernova. It was by a big rock that fell on their head. But although it is an example of death from above, but there are other mass extinctions even worse than the dinosaurs, and it would be interesting if a supernova had anything to do with even one of them. Okay, so what would be bad about one of these? Well, it turns out there are a couple of things. So one of the obvious things is so these supernova explosions are full of nasty high energy particles. The fancy name for this is neutrinos. And there's been an idea, but what if these nasty particles would be bad for us? And that would be very bad. Fortunately, that turns out to not be the main problem. The real problem is the supernova emits a bunch of X-rays, gamma rays, really nasty stuff that you don't want to get zapped with. And the good news is we don't get zapped by that. The atmosphere shields us from the really nasty X-rays, gamma rays, ultraviolet light from the supernova. But the bad news is although the atmosphere shields us, it is damaged badly. And the supernova destroys the ozone of the Earth. So this is a little cartoon of what the Earth looked like, whatever that is, 13 years ago. There's this nasty hole, this is a map of ozone, and there's none over the South Pole. That's bad. This is the ozone hole. That sense is cleared up because we stopped using stupid spray cans. But I'm not talking about a little hole. I'm talking about no ozone at all. And that's bad news because, so what does ozone do for us? Why do we like ozone? Care to guess? We need it. We want it. It's a good thing. It protects us from ultraviolet radiation, which comes from the sun. So without ozone, we lose our shielding from ultraviolet light, which comes from the sun, and then it's the sun that does the killing, because then the ultraviolet light from the sun is unfiltered, and that's the nasty stuff you have to watch out for at the beach. Or when you're sunning yourself. And so you and I would put on our sunblock 2000 and a big hat, but small beasties at the bottom of the food chain can't do that, and then they die off, little microscopic plankton and so forth. And then the trouble is that once they die off, they're at the bottom of the food chain, and the things that eat them die off, and the things that eat them, and pretty soon that's not funny anymore. And so that's what can cause a real damage. All right. So, good. So that's why a supernova is dangerous. And so when you think about this, it turns out that you can work out what the minimum safe distance at which you want to have one of these things, and inside of that it's not funny anymore. And the distance is about 30 light years. That is, the distance light moves in about 30 years. And the important thing to understand is the nearest star to us is about 4 light years. So what this says is this is very, very near the Earth. And anything further away than that is fine. So unless you have something extremely close, you're safe, and we are safe tonight. But over the history of the Earth, it's very likely that we've had a supernova this close. All right? So here we go. So now for the big finish. So I've explained what a supernova is. I've explained why they're dangerous. And I've explained it's likely that over the history of the Earth, we have had supernova near us. So the question is, how would we know? Because science is about evidence. What evidence can we find that can convince us that we had a supernova near the Earth? So we want to do supernova archaeology, and this thing, which is a nuclear accelerator, will be an important tool. So here we go. So how do we know that there was a supernova near the Earth? And it turns out the smoking gun is the smoke, that is the stuff made by the supernova, which will get delivered to the Earth. The supernova explosion debris, the guts of the star, get delivered to the Earth. So the idea goes like this. This is another picture of a beautiful remains of a supernova explosion. This is material that was launched from an exploding star at a few % of the speed of light, enormous speeds, flying out into space, but also sweeping up the thin gas of interstellar material that lies out there between the stars. So as this blast spreads out into space, it gradually sweeps up material and slows down. And the only thing protecting us from this nasty blast of material is the sun itself. Now the sun's the good guy. So this is an image of the sun, except I blocked out the sun itself so you can see the light around it. And you can see the sun is blowing this gentle breeze of material. We call it the solar wind. So there's a flow of material out of the sun, and then there's nasty supernova blasts coming towards us, which means there's a collision of the blast from the supernova, the wind from the sun, and they collide with each other. And it's a competition, and it's a question of who wins. And if the blast is close enough, if the supernova is close enough, it still is a very powerful blast. It overwhelms the solar wind. It pushes the solar material all the way back inside the Earth's orbit and dumps supernova material on the Earth, and it literally rains down. Supernova junk rains down on our heads and accumulates in natural archives like sea sediments and ice cores. And then the question is, okay, fair enough. So if all of that happens, still, how do we know? How can I dig up something from the bottom of the ocean and say, yes, I know this came from a supernova? And so that's still a hard problem. So we thought about this. We need a fingerprint from the supernova, and then you think about the fact that there are these nuclear reactors, there are these element factories. So what we don't want is something that's stable and happy and a nucleus or atom that stays by itself and doesn't do anything. What we actually want are some of these unhappy, eager to change radioactive nuclei. The beauty of them is because they're eager to change, they decay and go away. So if you found something that hasn't changed yet, hasn't decayed, that means it had to come here recently before the clock was up and it decayed away to something stable. So if you find it, something had to put it here because whatever was born with the Earth is gone. So finding radioactivity that hasn't decayed away, that's the key. So just to give you a sense of what this would be like, so this is a computer simulation. We're going to take the solar system and hit it with a supernova explosion. So this is the sun. So I'm going to have a computer simulation. This is the sun. The coloring here is the solar wind. It's the thing I just showed you in the movie. It's gas moving away from the sun, and the different colors means it's getting less dense as it moves, spreads out when it moves away from the sun. So it's the gentle breeze blowing off the sun, and then I'm going to zap it from a supernova from underneath, and that's what it looks like. And so I zap it from underneath, and the supernova pushes the solar wind back because it's this tremendous blast. And then I've drawn a little circle here. I didn't draw the Earth here, but if I did draw the Earth's orbit would be there. And you see that then the Earth is going around and around and finds itself directly inside supernova material. Now that's for a supernova that's very close and very dangerous, but it gives you the idea. Okay, so we want to look for supernova debris at the bottom of the ocean. And the amazing thing is, we have some evidence for this in this thing. All right, so this is a picture of a crazy thing. It won't take me long to explain what it is because this is all I know. It's something called a ferromanganese crust. So this is a weird thing. This picture is a picture of what one looks like as a coin for scale. The coin is basically the size of $50, so it's about that big. So the picture on the screen is too big for the size of the rock. It's something you can hold in your hand. Okay. So this thing that it's from the bottom of the ocean, and geologists know, we have a geologist in the room, they know all about these things. They're rocks at the bottom of the ocean that grab atoms from the water, particularly iron. They love iron, and manganese, another kind of heavy atom. They grab on, they lock on, and then they slowly grow over time. It's like tree rings except manganese and iron. It's weird stuff, but that's what happens at the bottom of the ocean. And they grow very slowly, so they add layers of manganese and iron atoms at a rate of 1 millimeter per million years. So these are tree rings that grow very slowly. But the idea is this thing, again, it's a rock about this big, and it has many millimeters, which means you're looking, as you dig down into it, you're looking many millions of years in the past. So it's like tree rings, it's like a fossil record. And so what you do, or what these amazing German scientists did, were to use ultra-high sensitive measurements to look for needles in haystacks. And they looked at one of these rocks, and lo and behold, there we go, they discovered that there was live radioactivity present in the form of this thing called iron-60, a particular kind of radioactivity that only lives for a few million years. And as they dug down, they found an interesting pattern. And you might ask yourself, what pattern do you expect to see? So this rock is supposed to be growing and growing, minding its own business, and a supernova happens, and then the rock continues to grow, minding its own business. So if you think about that, what you would expect to see is this. As the rock's growing, forming more layers, boring, 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 supernova, boring, boring, boring. Except at the beginning, our geologist friends didn't trust our nuclear physicist friends. They didn't give them a particularly good rock. It wasn't very level and well stratified. And so what they actually found is they found iron-60 in multiple layers, which is kind of weird. They could only slice it into 3. They found some evidence for iron in all 3. So that was a little peculiar. So the good news is we found this live radioactivity, but the geologists didn't have a very good rock, so we couldn't figure out where it came from in time. But then that changed about 12 years ago. Our same Germans then got a new one of these crusts from a different place in the Pacific Ocean, and it was much better layered, it was a much better rock, and then they found this amazing result. So let me show you, let me show you what you're seeing. So what you're seeing here is this is a graph, one graph, but it's such an amazing graph once you understand it. This is amount of radioactive iron, so no radioactive iron, and this is how long ago in the past. So you're digging down into the rock, so the top is today, this is 2 million years ago, 4 million, 6 million, 8, 10 million years ago. So you're digging down into the rock and asking, do I see radioactive iron? And the answer is no, 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 yes, no, 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 no. Well, that's exactly the signal we want. And so this bump here is telling us that lo and behold, not only is there radioactive iron, but it comes from a very particular time. If you read it off, it's more than 2 and less than 4, so it's about 2 to 3 million years ago. So we found a pulse of radioactivity at the bottom of the ocean, and that's really an amazing thing. There is radioactivity at the bottom of the ocean 2 to 3 million years ago, and it wasn't born here, it had to be brought here from space. That's an amazing thing.
excellent.
Oh, and by the way, you guys can't see this, but the measurements they're making are truly exquisite. For the experts in the room, they're measuring things at parts in 10 to the 15. It's absolutely magic. Okay, very good. So, we find live iron from the bottom of the ocean. That's amazing. And so that tells us we had a supernova nearby. And a good question is, well, wait a minute, did it leave any traces? Where is the rest of the remains of the explosion? And the answer is we live there. The sun lives in a region, the whole solar system lives in a region, our nearest neighbor in the galaxy, our local neighborhood, our backyard, is a region of very hot, very low density gas. It's called the local bubble. So it's basically a bubble, so not a lot of gas, but extremely hot. It's a big hot cavity. And the people the astronomers who study this, without knowing anything about crazy radioactivity, said, look, so to blow a bubble like this, you need a bunch of supernova explosions to occur over the past 10 million years. So it looks like we're finding radioactivity from one of the more recent and nearby supernova explosions. And they even have an idea of where it might be in the sky, the particular constellation. Also, another thing that's very cool is, if you think about it, the supernova explodes and throws its guts into space, including this crazy radioactivity. And the supernova debris gets more spread out the further away you are. And that means the further away you are, the less radioactivity comes to you. And so that means you can relate the amount of radioactivity you see, the amount of this crazy iron-60, to how far away the supernova is. For the experts, it's just an inverse square law. And so that means if I know how much iron I have, I can learn something about the distance to it, and through the miracle of modern algebra, I can solve for the distance, and I find that it's relatively close. It's 60 to 300 light years, which is not so close. Remember, 30 was the distance to kill you, and it's further away than that. So it's further than the kill distance, but not by much, so it's a near miss. And in fact, so this is an artist's conception of one of our ancestors seeing this thing exploding in the night. It's this gorgeous blue light. And there's some question about whether this wasn't an extinction event, but whether it still had biological impact. Maybe it could have had an impact on the climate, and maybe it had an effect on extinctions. Not to kill off huge numbers of species, but it might have been responsible for some biological die-offs. And people in this audience are experts on this, and they're looking at this as we speak. And that's really an amazing thing, because it tells you that, we aren't just citizens of the Earth, we're also citizens of the cosmos, and sometimes the cosmos intervenes in our lives. And once in a while, maybe it intervenes with a vengeance. So, very briefly, so I'm almost done, don't worry. So Adrian mentioned that there's been a lot going on this very month. And so I'll just briefly tell you a couple of things. We're still trying to understand it ourselves. There's now new data. I told you about the old data. There's now new data, more data from the deep ocean. So now, a different group of scientists from a different part of the world, in Australia now, have verified all the results that I already showed you. They verified that they're true and more. And they absolutely confirmed that there's this radioactivity 3 million years ago at the bottom of the ocean. They now also say there's some evidence for another supernova 8 million years ago. It's not as certain, but it looks like there's evidence for a second supernova. And they now measure the time history, so they can tell you how the radioactivity came over time, which tells a lot about what created it. And there's now a detection of supernova radioactivity from the moon. Because when we went to the moon in the 60s and early 70s, the Apollo missions, there were samples taken where we just drilled down into the moon. People literally had a little core sample taken here. So this is Alan Bean in Apollo 12, literally taking a core sample, and one of these is exactly the one that was studied, and several others as well. And lo and behold, there's evidence for supernova radioactivity from the moon as well, which makes complete sense, right? If there's supernova debris that's slamming into the Earth, the moon is in basically the same place, so it should also be on the moon. So it's a very beautiful confirmation. And there's other interesting things to be done with it as well. So we've come to the end. So let me summarize where we are. So live radioactivity has been seen multiple places across the bottom of the ocean, and we know that it came from 3 million years ago, and now there's evidence for 8 million years ago as well. And so this is the birth of supernova archaeology, and one of the beautiful things about it is how it draws together so many aspects of science. It's not just about astronomy, it's also about physics, the nature of how these stars explode. It's about astrobiology, the connection between astronomy and biology, and even biology itself. I mean, there might have even been consequences for the development of life on Earth, maybe even for the development of human life. I wouldn't want to leave you with the impression there's nothing left to do in this subject. So we'd like to better understand how these supernovae impact the solar system. We'd like to understand how they make radioactivity. We'd like to find other kinds of radioactivity. This radioactive iron is not the only kind of radioactivity out there that's interesting, and there are other kinds of radioactivity that we'd really like to see. We now have evidence for the moon, so we'd like to see that in greater detail. And ultimately, all of this was for a supernova that was relatively recent, just 3 million years ago, bat of an eye in the history of the Earth. And the interesting question would be, is it possible now to reach back further in the past and to check for a supernova when we know there was a mass die-off of species, a mass extinction? And the interesting thing is that that's now a possible thing to do, because what this all the results today have shown us is that now we have the technology, we know how to do this, we have the ability to make the real measurements, to do real science, to check whether a supernova exploded deep into the past history of the Earth. And we certainly don't yet know whether a supernova had anything to do with any mass extinctions, but now we have the technology to really answer that question in a serious way. And that's an exciting thing. So stay tuned, there's going to be more. Thanks very much.